Classical mechanics, electromagnetism, general relativity, the behavior of fundamental particles, all of it can be replaced by a single, simple mathematical rule. We are usually taught to view physics through a local, step-by-step mindset. In this view, the universe is a mechanical machine driven entirely by differential equations, and the immediate physical forces acting on an object right at this very moment. If you want to use Newton's second law, force equals mass times acceleration, you have to calculate the events of every single microsecond based exclusively on the forces present in the microsecond right before it. But calculating everything from the bottom up might be exactly backwards. The math suggests there is a global rule that governs physical reality from a top-down perspective. To see where the standard Newtonian mindset starts to break down, we can look at a classic physics stress test, the double pendulum. Take a look at this double pendulum. Calculating the exact forces for this system is a nightmare. As the top pendulum swings, it constantly changes the point of attachment for the bottom pendulum. That means the second pendulum exists in a reference frame that never stops moving. Tracking that clunky, highly sensitive movement requires writing complex equations for force equals mass times acceleration, recalculating those vectors over and over as they rapidly shift direction. Calculating exact vectors is simply too difficult for complex systems. To accurately model how reality moves, we need a way to look at the behavior of the system as a single whole. In June of 1696, the mathematician Johann Bernoulli sent a challenge to the world's greatest minds. He asked them to find the shape of a ramp that would allow a sliding mass to travel from point A to point B the fastest, a puzzle known as the brachistochrone problem. Bernoulli solved his challenge using a highly creative approach. Instead of using mechanical forces and gravity, he treated the falling mass like a ray of light passing through layers of varying density, accelerating as it went. As we can see in this animation of Fermat's principle of least time, light refracting through a new medium, like water, does not take the shortest physical distance. It bends to take the path that requires the shortest amount of time. Bernoulli applied this exact optics principle back to his physical ramp. He proved that the optimal path for the falling mass matches the exact same geometry light uses to refract, a shape called a cycloid. Abstract light and physical matter share the exact same optimization math. Nature possesses a hidden budget, always balancing acceleration and path length to calculate the absolute most efficient route. In the 1740s, Pierre-Louis de Maupertuis proposed that nature optimizes a foundational quantity he called action. He defined this action simply as mass times velocity times distance. Look at this simple example of a half-kilogram ball rolling across the ground. If it moves 6 meters at 3 meters per second, that generates 9 units of action. If it bounces off a wall and travels the same distance and speed, the total action for the trip sums up to 18. Maupertuis claimed that out of all possible bounce trajectories, the physical ball will always follow the one that minimizes this total action. But he couldn't mathematically prove it, and there was no obvious physical reason why nature would care about that specific equation. This visualization shows the mathematical rescue provided by Leonhard Euler and Joseph-Louis Lagrange. To prove Maupertuis right, they tested infinite possibilities by taking the optimal true path and adding a tiny theoretical wiggle to it, which they called eta. They found that if you are sitting squarely on the true path of least action, any tiny wiggles you add effectively cancel out. The difference in action between the true path and the slightly wobbly path becomes exactly 0. Euler and Lagrange proved nature doesn't just guess its path, it adheres to a strict global law dictating that the variation of action must be 0. In 1834, William Rowan Hamilton updated the math into its modern form. Instead of integrating mass and distance, Hamilton's principle integrates kinetic energy minus potential energy over a specific period of time. This equation represents the Lagrangian. By subtracting the potential energy from the kinetic energy, it functions as a mathematical machine. You feed it the energies of your system, and it cranks out the perfect equations of motion. Energy values are scalars. They are just simple amounts with no direction. By relying on scalars, you completely remove messy, complex directional vectors and forces from the math. Returning to our double pendulum, we no longer need to calculate shifting reference frames. By simply plugging its kinetic and potential energy into the Euler-Lagrange equation, the system solves its own motion effortlessly. We no longer have to build a system from the bottom up, using localized forces. Complex physical systems are perfectly understood through global energies. There is a crucial mathematical caveat here. The rule does not guarantee a true minimum value every single time. It is more accurately called the principle of stationary action. Setting the derivative of the action to zero guarantees you find a stationary point. That stationary point is the only mathematical condition required to generate the correct laws of motion. Bernoulli already showed that light and matter share the same math. Because this rule focuses on the state of a system, its energy, rather than the direction of a force, it scales up. It allows us to describe the curvature of a galaxy or the propagation of an electromagnetic field using the exact same framework as a simple pendulum. By the turn of the 20th century, this transition away from classical forces provided the conceptual foundation for modern quantum mechanics and the study of the atom. The universe does not operate as a clunky, localized machine being pushed around by forces. It is a profoundly elegant system, optimizing its budget from the top down.